Welcome to the third video in the computer vision crash course. In the last two videos, we looked at how we deal with images in Python, how we can manipulate the images in NumPy, what the different dimensions are, and what the color space is meaning, and how we could use Pillow to visualize the images in the Colab notebook. In the second video, we looked at how we can use our Colab notebook together with Git to version our notebooks. And we also looked at how we can upload custom files to the notebook instance and access them from the code. In this video, we're going to explore the dataset that we will be using for the image classification. And we will use the scikit-learn digit dataset. And we will classify images from 0 to 9. And that's what we're going to use in video number 4. We're going to actually train the model that does the digit classification and evaluate the model and see how we can see how well the model is performing. And in the 5th video, we're actually going to use the model to make our own predictions on our own images. So let's head over to the notebook. And in the last video, we set up this Git repository. So I'm going to click the link to open my Colab. And actually, I'm going to create a new notebook. This new notebook, I'm going to call digit classification sklearn. So the first thing we're going to do is that we're going to import sklearn. Sklearn is a library, a Python library for machine learning purposes. So it includes some dummy datasets and a lot of different machine learning models that are very easy to get started with. And most of them share a very similar API, so you can very easily switch between different kind of models and see which one is performing the best without making a lot of code changes. So second, we're going to import datasets. So we're going to import sklearn.datasets and just name it as datasets. And next we're going to use the download the data. So we're going to do datasets.load digits. This is a dataset that is already existing in sklearn. If we do type of data, we can see that it's a sklearn bunch, which means that we can do data.keys, and we see what different kind of data is there in this actual object. And what we are interested in is images and targets. So this is our input data to the model, the actual images, and this will be our ground truth labels, what actual digits they are containing. So if we want to know more about this, we can just Google for sklearn digits datasets, and we can go to the documentation and see that this loads a dataset which contains of 8 by 8 pixel images. So that's really tiny images. We have 10 different classes. So that is, of course, the digits 0 to 9. We have approximately 180 different images for each digit. And total number of images are 1,797. They have a dimensionality of 64, which is 8 by 8. And the features, the pixel values, are integers between 0 and 16. So in the first video, we said that the common way to represent images is 0 to 255, but in this case, they have instead 0 to 16. So let's go back to our Colab notebook, and we do data.images. And let's take the length of this. So we see that, yes, it's indeed 1,797 images. So if we address the first of these images and we write the type of it, we can see that this is an NumPy n-dimensional array. So let's print the shape of this. And yes, indeed, it's an 8x8 image. So if we just do like this, we can see the actual pixel values. And from this, we can almost guess what digit it is. We can see that it's 0 on the edges and it's 0 in the middle. And then we have a bit brighter values here around in kind of a circle. If we write the targets for the 0th index, we can see that, yes, it's indeed a 0. But we still want to visualize this in a bit better way. So what we can see here is that we have a dot, so it's floating point. We can verify that by typing dtype. And yes, we see that it's float 64. We can also see that the values are between 0 and, kind of like a bit more than 10. And according to the documentation, it was going to be 0 to 16. So let's actually import NumPy as np. And we can print the maximum of this whole array. And yes, it's indeed 16, as the documentation say. So since we're normally working with 0 to 255 when we want to visualize images, I'm going to divide this by 16, so we get a maximum of 1, and then I multiply by 255. And now we have values between 0 and 255. And I also said in the first video that we normally use images as uint8, 8-bit unsigned integers. And this is a floating point for the two. So for now, let's do as type numpy.uint8. And here you can see that now it's an uint8 with values between 0 and 255. So this is good for visualization, but when doing machine learning, we typically want to work with floating points, at least for the training. So we're going to work with these images both as floating points and as uint8. If I now want to visualize this, I can from field import image. This is also from the first video. Image.from array. And this is a grayscale image since we just have one dimension in the depth. As I said in the first video, the mode for that is L. This was very slow. Not sure what's going on here. So we can always choose to restart the runtime. And this will clear the state. So now we have to rerun the different cells. Now we can see that the instance is initializing. So we actually get a new instance now after doing this. Now we can see that the instance is up and running again, and the first cell is executed. Second cell, third cell. Now we can see that it does work, but we haven't at this point imported NumPy yet. So let's move the import up here, rerun that cell, and now we can run this cell again. Now we see that we have a tiny 0 here. So that is a bit hard to see. So for visualization purpose, we want to resize this image. And let's do it 100 by 100. Doing this, we see that we get a very fuzzy image. And this is actually not what it looks like in the original format, since when we upscale it, it will automatically do some kind of linear or bilinear normalization of the pixel values, or interpolation of the pixel values. So we can change that by setting resample equals to image dot nearest. This is basically what the image look like. We just get bigger pixels. So let's create a variable for the index, and we print the data.target. So what kind of digit is it actually in the image? And we do that for I, and we do the visualization for I. If we rerun this, we will get the same image, and we see that the ground truth should be a 0, or is a 0. If we do this for index 1, we get something that kind of looks like a 1, and it should be a 1. If we do it for 9, we get a 9. So what about 10? Now we see that the ground truth value has gone to 0 again. So this is the second 0 in the dataset. And we can do it for 100. We see that index 100 is a 4. And this is an image of a 4, a little bit hard to see. I would just as well guess for a 9. So I guess with this low resolution, it will be hard to get perfect accuracy on the models, but we'll see that in the next step when we train the models. So what have we learned now? We have learned what the different images looks like, how we can visualize them, how we access them in this bunch, and how we access the ground truth value, which tells us what we are actually looking at in the image. And we have also seen the rescaling that we need to do to visualize them. And we will use this in reverse later if we want to, if we train a model on the floating point 64-bit values with a maximum of 16, and we want to classify an image which we have uploaded, which has 255, then we will need to do this transformation in reverse. So that's for the later videos. So for now, what I'm going to do is to save this, because now I have something that I'm quite happy with for the first step. So just as in the last video, I'm going to save it to my GitHub account. And I created this folder where I save the infrastructure file. So I'm just going to copy this path and paste it here. and I give a commit message and save the file. So now we can easily access this file again in the next video, where we're actually going to continue to train a model on this data.